All right. Hello, everyone. Thanks for those of you that are here right now. Um, so I'm going to be doing a live lecture, going over questions and then explaining certain concepts about kinematics, energy, and thermodynamics. Um, All right, so this is the consent to audio form. So basically, this is just stating by logging in and participating in this that you are giving your consent to be able to post this publicly on our website and for this to be online. So in that case, we encourage you to kind of change your name and change your picture if you haven't done so already. All right, and then here I have linked our GroupMe where you're encouraged to ask questions, collaborate. We also have linked here our Instagram and then our YouTube where we post all of our content. And then as a reminder to everyone, we'll have 2 lectures a week. So Sunday we'll have the recorded lecture that'll come out after this class actually. And then a live lecture that we are starting tonight, and that'll begin at 8:30 on Mondays. All right, so our first question here will be kinematics. So the way that this will all work is that depending on the question, I'll give everyone 1 to 2 minutes to answer, and then I'll also open a poll here so you guys can input your answers and I'll be able to see them. And then we will discuss the questions and then we'll discuss the concepts behind the questions. Also, I wanted to make a point to make sure that everyone is answering these questions like you are answering questions on the MCAT. So take your time, be careful when reading all the questions. It is also helpful if you predict an answer before you go into the multiple choice questions. So you're not getting distracted by the answer choices and then going through a process of elimination, going through the rest of the choices so you can end up at the correct answer. So we will begin, and on this question, I will give everyone 1 minute. All right, it looks like most people got their answers. I'll give a few more seconds and then we'll go over. All right. So the answer to this question is B, distance. So B is the only one here that is a scalar quantity and not a vector quantity. If you did not get that right, it looked like actually everyone that answered it did, so that's great. Um, I also will discuss just the difference between vector and scalars, and then in the case of for displacement and velocity, and then its scalar component of distance and speed. I will discuss that in the next few slides, so we can go over that. All right, so scalars are quantities that have a magnitude, but they don't have a direction, while vectors have a magnitude and a direction. So an easy way to kind of see the difference between them is when looking at displacement and distance. So as you can see kind of in the right corner of your screen here, for distance, you can see that the path traveled matters. So going along this kind of curvy path here and ending up somewhere, that is our distance value. So it's not really mattering what direction that we're going, but just the magnitude that we got here. For the displacement, we are just ending up in one spot and then considering the next spot. And so we're considering both our magnitude and our direction here. And there's other values like for scalars, besides distance, speed, you have work, power, also scalars. And for vectors, we also have force and torque that are also vector quantities. All right, so specifically about some kinematic variables here. So we talked a little bit about displacement, but what displacement actually is the final displacement minus the initial displacement. And also the fact that it is different than distance is important in terms of kinematics and just using the correct variables in the equations. For velocity, we use V to denote that, and we also measure it in meters per second. Velocity is basically our rate of change of displacement, and it's telling us how fast we are going. For speed, this is different than velocity, as it's kind of the same thing for displacement and distance. So speed only has the magnitude, while velocity has a magnitude and a direction. It's also important to note that average velocity and instantaneous velocity are different. So average velocity is that equation that we just defined as velocity is equal to our displacement over our change in time, while instantaneous velocity is just our velocity at a given point in time. In terms of acceleration, we denote that with an A, and that's measured in meters per second squared. So acceleration is, in terms of its equation, is delta V, which is velocity, so the change in velocity over the change in time. So it's telling us our rate of change in velocity, or how fast our velocity is changing. All right, so moving on to our second question. This one is also a kinematic question. It is a calculation though, as you can see, so I'll give you a little bit more time. Whenever you guys are ready, go ahead, start reading, and I will start timing 2 minutes. All right, it doesn't look like we have any responses yet, so I'll give you, we got one. I'll give you guys a little bit more time. All right, so I'm going to end the poll in a few seconds here. All right. So on the next slide here, I'll show you guys my work and then go over how to approach these certain types of kinematics problems. So in this case, the answer was A. All right, so this is kind of a visual representation here of what was going on. I think on the next slide here, I have more of my work. And then, so in this case, we have, you can see the final velocity is what we're trying to find. We also know our initial velocity because the problem says that we are dropping the ball, or this guy over here on the side is dropping the ball. And then we also know the final displacement, which is going to be 80 meters. And we also know our acceleration due to gravity, which you can approximate as 10 meters per second squared. So using our kinematic equations that I'll show later on as we're going through some more content, this is one of the kinematic variables that is important to commit to memory. And once you do that, you can be able to figure out which ones you do need based on the variables that you do have, and also the variables that you are trying to find. All right, so here is a look at the problem specifically. So these equations right here are 5 important kinematic variables to commit to memory. The reason why they're important to commit to memory is because each one is missing one of the kinematic variables. So in a problem like this, where I have, let's see, yeah, so I have, I know final velocity, I know displacement, but there's a certain thing I don't have, and I don't have my time. So I don't have the time taken for this ball to drop 80 meters. And therefore, I know that I know all of these other equations have time. So I can use my last equation here in order to solve for my final velocity. And then at that point, it's kind of just plugging in all my answers, or all my variables into the equation, and then solving. All right. So these are the kinematic variables here that I was just talking about. And you can see how each one is missing one of the variables. And then I'll also talk about some common applications that you might see these in. The one example that we just did was free fall. So that is when an object is falling and it's only accelerating due to the influence of gravity. This example here with this cannon shooting a projectile is also a form of free fall, but it's specifically projectile motion. And this is an important case because we are having movement in both the X direction and the Y direction. So as you can see here, the projectile is moving both horizontally and it's falling due to the influence of gravity. In problems like this, it's not only important to define your positive and negative values, like maybe you would want to define going down as negative, so you can keep gravity positive, but you also want to define your X and your Y components and then solve those separately. That just makes your calculations a lot easier. And especially on the MCAT, when you don't have that much time, it is important to save time and make calculations more simple. All right, so we're going to move on a little bit from kinematics and just go into a force problem here. So I will give everyone 1 minute to solve this problem. and then answer your answer choices in the poll, and we will discuss them. All right, so it looks like everyone's answered here. So I will end the poll and talk more about this problem. So as you can see, the answer to the question was -10 newtons. And this is because of Newton's third law, which states that for every force, there is an equal and opposite force acting against the that same object. So because we had an object that was exerting a normal force on the ground of 10 newtons, the force that is now exerted by the ground on the object, which will be equal and opposite, will be the same magnitude, but just opposite direction. So this is kind of an example where kind of differentiating between vectors and scalars becomes important. And then now I will also talk about the other Newton's laws and then some important forces that are important to know for the MCAT. So first off, we have Newton's first law. So this is kind of one of the general ones I feel like people know. So it's when an object is at rest and it'll stay at rest. And when it's in motion, it will remain in motion unless acted upon by a net force. The point of it being acted upon by a net force is an important thing to note, because it's not just any force that will cause it to maybe change its direction or change the magnitude of its displacement or velocity, but it's because it's a net force acting on it. If you have two forces that act together and cancel each other out, this will not cause any change in motion, or it will not cause something to move if it was at rest. Considering Newton's second law of motion, so this is seen, and you can look at this equation here, and it's basically the definition of force, so which is mass. It's the mass of an object times its acceleration. So if the net force acting on an object with a mass of m is a non-zero number, the object will accelerate or decelerate. And then it's also important going through any type of physics problems to make sure you're keeping your units in check. So force is measured in newtons, and that is kilograms times meters over second squared. And then as we talked about force, or for Newton's third law, so the force of an object A on an object B is going to be equal and opposite to a force of B on an object A. All right, and these are some forces in particular that are important to know for solving problems that you might come across. So for an inclined plane problem, for example, you will have to know how to deal with gravitational force, which is essentially the weight of an object. So as you can see here, if you looked in the inclined plane problem, the force vector for the weight of this object is the one going straight down here. While for a normal force, which is always the force that opposes the surface that it's on. So here for this block on this ramp, it's always going to be perpendicular to the surface that it's on. And so that doesn't instead act, I guess, straight vertically. It always acts perpendicularly to the surface that it's on. For centripetal force, so this is kind of a different type of force that occurs when there's a force vector that is pointing inwards for the entire time that an object is moving. So instead of force being mass times acceleration and easy like that, for the centripetal force equation is velocity squared times mass and over the radius of the circumference that the object is rotating in. Additionally, the force will cause an acceleration inward, and that equation is acceleration equals velocity squared over the radius. And one thing to note about centripetal force is that it's instantaneous velocity vector. So you can see kind of in this picture, the velocity points tangent to wherever the object is moving. And if all of a sudden we did not have a force going inwards, our object would move just completely tangent to this line. And if it's not acted upon by any other force, then it'll just keep going in that direction that is tangent. All right, before I move on to the next question, does anyone have any questions about anything that we have talked about so far? You guys are welcome to unmute or use the chat if you want. All right, perfect. All right, so the next question is about energy. So I will, again, give you guys about a minute, maybe a little bit longer on this one, and then we will talk about it and make sure to put your answers in the poll. All right, I will end the poll if everyone is ready. All right, so this question says if the gravitational potential energy of an object is halved in the absence of non-conservative forces, which of the following must be true, assuming the total mechanical energy of the object is constant? So initially, there's a few things to be aware of, and it's knowing what non-conservative forces mean, and then also that knowing what total mechanical energy also is, that it's being constant. So if we're not regarding non-conservative forces here, that would be forces like friction or drag or air resistance that dissipate energy. For conservative forces, those are like forces that we talked about, like the force of gravity, also like electrostatic force, which we won't talk about today, but another example of a conservative force. So knowing that our energy would be constant, it's just that it's not changing. So when approaching this problem, looking at A, so the object has been lowered to half of its initial height. So if we use the equation here that we know for potential energy, which is mass times gravity times height. So if it was half of its initial height, this could possibly be true, but it does not have to be true. The same thing is true with D. So if the mass is halved, the mass of the object is halved, then it also could be true, but it does not have to be. And then when looking at B, it looks like it could be right, but the point is of knowing the law of conservation of energy and total mechanical energy being constant. So it's not the fact of kinetic energy and potential energy equaling total mechanical energy, but it's the difference between each one making the total energy of the system being constant. And if that doesn't quite make sense yet, I'll explain it a little bit more in the next slides. So hopefully it'll make a little bit more sense. All right, so first I'll talk about potential energy a little bit more, as well as kinetic energy. So potential energy in terms of potential mechanical energy, there's two different types that we have. And potential energy is essentially just the energy that is associated with an object's position. So for gravitational potential energy, as we talked about the equation, is U equals the mass of the object times gravity, and then times the height or the displacement that the object has fallen. And then for elastic potential energy, so this is the potential energy of any spring-like object, and that equation is U, which is potential energy, equals to 1/2 times K, which is a spring constant, times x squared, and x is the basically how far the object has displaced from its equilibrium position. So for an object that has a high K, that means it has a high spring constant, and it's hard to deform, and that makes it have a larger potential energy. And then that also would make it harder to displace and get it away from its equilibrium position. And then also thinking about units for energy, our units are going to be joules, which is kilograms times meters squared over seconds squared. And then kinetic energy, which is a very big point in physics and something to really be conscious of all the time, is the fact that it is associated with the motion of an object. So it's the energy associated with that, and its equation is K equals 1/2 times the mass of an object times its velocity squared. All right, so here's when I'll talk a little bit more about what total mechanical energy is and also the conservation of energy. So when we are thinking about conservative forces, we are not thinking about energy dissipated. So we're not taking friction into account, any other forces like that. And if that's the case, then our total mechanical energy is going to be equal to our potential energy plus our kinetic energy. And then we can also use that to say that energy is never created or destroyed when we think about the change in potential energy and the change of kinetic energy. So the change of kinetic energy and potential energy added together is just going to be zero when we just have a conservative forces involved. But when we have non-conservative forces involved, this will cause a non-zero value to be the answer, as there's just energy that isn't accounted for. Whereas when we are just dealing with conservative forces and just kinetic energy being transferred into potential energy or potential energy being transferred into kinetic energy, then we don't have to worry about the energy being dissipated elsewhere. All right. Does anybody have any questions about that one? All right. So this is a question about the work energy theorem. So I'll give everybody a minute and then we will go over the answer and then discuss more about that. All right. Looks like everyone answered here, so I will close the poll and we will discuss. All right, so the question is, which of the following best defines the work energy theorem? So if we're looking at the questions and then going to figure out which one's wrong, going through process of elimination. So A here, so the work done on an object is the process by which a quantity of energy is moved from one system to another. So this is actually the definition of what work is, and not the work energy theorem specifically. So work isn't energy, although it is measured in joules, so you would think that it might be. However, it is also just the transfer of energy. It's what does it is what transfers the energy. When looking at B, so the total work done on any object is equal to the change in kinetic energy for that object. And that one does make sense. So I'm going to leave that for now and then look at C and D. For looking at C, so the total work done on any object is the power emitted by a system multiplied by time. So it doesn't look like anyone answered this one. And this is essentially just relating power and work. So D, on the other hand, so the work done on any object by any force is proportional to the change in kinetic energy for that object. So this one would be kind of hard not to pick. So yeah, so it's because the total work done on an object is equal, and it's not that it's proportional to the kinetic energy. Additionally, it's the net force that relates to the work done on the object. So now I'll talk about work, torque, the work energy theorem a little bit more, as well as power. So work, the equation for work is FD cosine theta. So F as in force, D for displacement, and then cosine theta. So the fact that it is cosine theta, we know that work always acts either parallel or anti-parallel. So, and as I was saying earlier, so the work is the process of transferring energy from one system to another. And then work is also measured in joules. Although it's not energy, but it's just the transfer of energy from one system to another. So make sure to not confuse that because it does have similar units. All right, and then torque. So torque is the lever arm multiplied by the force. And this one is multiplied by sine theta. So as work was multiplied by cosine theta, it's always acting parallel or perpendicularly to the object, whereas torque is acting perpendicularly to the lever arm that it's working on. And this makes sense because torque is the force that causes an object to rotate. And this is measured in Newton meters. All right, so now talking about the work energy theorem. So this is a very important relationship because kinetic energy is something that is always seen in a lot of different parts of physics equations, and thus the chemistry physics part of the MCAT. And it basically just relates work being equal to the change in kinetic energy. It also is therefore equal to the negative change in potential energy. And then power is just the rate at which energy is transferred from one system to another. So basically just how fast energy is transferred between systems. And when looking at its units, that is measured in joules per second. All right, so I will switch gears here to thermodynamics. So if anyone has any questions before we move on, feel free to ask. All right, sounds good. All right, so this is a Roman numeral question. I'll give you guys a little bit longer than a minute to answer this one. All right, looks like everyone has answered here, so I will close the poll. All right, so when looking at Roman numeral problems, we want to start off with the Roman numeral that we see come up twice in our answer choices. And this will just make it easier for our process of elimination. So in this case, I would start off with Roman numeral 2, and that's because it shows up in B and C. So when looking at Roman numeral 2, I know it is not right because the kinetic energy of the molecules in the hot object will actually decrease. So kinetic energy and heat is always transferred from the hot object to the cooler object. So therefore it would be opposite. In that case, I can cross off both B and C. And from that, I know A is right. So I will look at 3. And so the two objects are in thermal equilibrium. So that is false because they are, it says they are at different temperatures. So we know their thermal equilibrium must be unequal. Eventually, they could get in thermal equilibrium where they're no longer transferring heat between each other. But in this case, at this time that they are not in thermal equilibrium. All right, so I'm going to talk about some um, thermodynamic variables here, just certain things to differentiate, as well as the zeroth law of thermodynamics and thermal equilibrium. So for temperature, we can think of temperature as um, being proportional to the average kinetic energy of an object. And temperature also is what determines the direction of heat flow, as I was talking about. So heat will always flow from the hotter object to the colder object. Um, and then on the MCAT, we measure temperature in Kelvin or degrees Celsius. So the conversion factor here is that Kelvin equals to degrees Celsius plus 273. So as like water boils at 100 degrees Celsius, that would be 373 degrees or 373 Kelvin. All right, and then heat. So heat is the transfer of thermal energy from an object with a higher temperature to an object with a lower temperature. And that unit is joules. And then additionally, heat, we also have, when thinking about heat, we can think of conduction, convection, and radiation, just different ways that heat is transferred. So what conduction is conduction is the transfer of heat through objects that are in contact with each other, while convection is the transfer of heat due to a fluid flowing over an object. And then radiation is the transfer of heat from electromagnetic energy. So like the UV sun rays, for example. All right. And then for the for thermal equilibrium, so defining that, it's when there's no net heat flow between objects that are in thermal contact with each other. So they don't necessarily need to be in direct contact, but like we talked about with convection and radiation, those would be in thermal contact as they're transferring heat between each other. And then the zeroth law of thermodynamics is basically the transitive property of thermodynamic systems. So it basically says if object A is in thermal equilibrium with object B, and object B is in thermal equilibrium with object C, then object A and C are in thermal equilibrium, meaning that they're not transferring any heat between them. All right, next question, also a thermodynamics question. So I will give you, yes, this one I'll give you a little bit longer. I'll give you about 2 minutes. All right, so I'll give about 15 more seconds here. All right, looks like we are good. So everyone got that one right, so that's great. This is a calculation one, so where we had to use this heat transfer equation. An important thing to realize in this problem is that it stated that we were assuming that no phase change was occurring throughout the process. However, if there was a phase change that was going on while the temperature was changing, then we would have to use a different equation. And that is because there's no temperature change during phase changes. So yeah, so this basically was a problem where if you figured out what to do, then you just plugged in your variables. All right, so yeah, so this is talking more about just those different equations in general, and also what specific heat is and what heat of transformation is. So specific heat is the amount of heat required to raise 1 gram of a substance by 1 unit of Kelvin or 1 unit of degrees Celsius. These two the values for specific heat, they are good to memorize. The one cal per gram times Kelvin is a pretty easy one, and then you also have 4.2 joules per gram times Kelvin. Additionally, for heat of transformation, so what that is, it's the transfer of thermal energy from an object with a higher temperature to an object with a lower temperature. And you use this when we are going through a phase change. And this is because we're not using this equation with, there's no temperature in it. So we wouldn't be getting 0 in our answer like we would with using our equation that involves specific heat. All right, so I will go over one more question here, and then I will go over if anyone has any questions. All right, so I'll give people a little over a minute for this question. All right. All right, so everyone also got this one right, which is awesome. So yeah, so for this problem, it's essential that you know the first law of thermodynamics. So here we have the change in internal energy is equal to heat plus the work that is either done to or done by the system. So in a adiabatic compression, this is when we don't have any heat transfer. So therefore, when we were looking at our equation here, our change in internal energy is equal to the work done. And then when looking at the multiple choice questions here, we can easily choose C as that is the only one that has 0 in the answer choice for heat. All right, so the first law of thermodynamics. So besides the question that we went over, one thing that is important in this equation is to know how to define heat and work in terms of being positive and negative. So sometimes you might see this equation with a negative sign instead of a positive sign. And that's okay as long as you're just defining the variables in a certain way. So for me, I think it is easier to make heat and to make work positive. And I'm just defining them as a way that Q is the heat going into a system, and then work is the work being done on a system. When making work, if you make work negative, then it would just be the work done by a system. And then internal energy, exactly what it is, it's pretty much the sum of the kinetic energies and the potential energies of the gas molecules in a system. And then also the different microstates and macrostates that these molecules can assume. And then lastly, for work, as you can see here, sometimes looking at pressure and volume graphically is, you'll see that on the MCAT. And it's important to know that the area under the curve is the work done for pressure and volume graphs. Now, looking at the specific thermodynamic processes, so we have pressure and volume, the same thing as we had on the other graph. And then we can see how it's affected when we have either isothermal, adiabatic, isobaric, or isochoric processes. So when our temperature is constant, when we don't have any change in temperature, we can relate that to internal energy. And since they are proportional, we can assume that the change in internal energy also be zero. And we know in that case that heat would be equal to work. Additionally, for a adiabatic process, no heat is exchanged. So as we talked about in our previous problem, we know that our heat would be zero, and thus our change in internal energy would equal negative work. For isobaric process, nothing really changes in terms of using the equations. And then for an isochoric process, our work is going to be equal to zero, as we will have no area under the curve when looking at our graph here. And then that'll make our change in internal energy equal to our heat. All right. So this will be it. If anyone has any questions before we leave, feel free to say something or message in the chat. Also, these videos will be available on YouTube. Also, the pre-recorded lecture that was made last night by Megan will also be on YouTube. And then continue to either use the GroupMe to ask questions, or you can also email us with any questions you might have. Yeah, question 1. Right. Yeah, so which of the following is not considered a vector quantity? So here we have displacement, which is a vector because it takes both magnitude. Oh, sorry. Yeah. Question 2. Yes. Let's see. Yeah. So in terms of the equations that all the kinematic equations that we want to use, there are those 5 that are important to memorize. So when approaching these questions, it's helpful if you draw out a picture and then kind of figure out what variables you have defined. So here I have figured out that I have my displacement's 80 meters. My initial velocity is 0 meters per second. And kind of a quick trick for that is when the problem says a ball was released or something was released, that you know that your initial velocity is 0. And our acceleration is due to gravity only, as it is a free fall problem. So that is 10 meters per second squared. And then also the only thing that we don't have is time, and we're trying to find our final velocity. So when I'm trying to use these 5 question or equations here, I know to use the last one in this case, since I don't have time, and I have the rest of the variables besides final velocity, which is what I'm trying to find. Also, another thing that might be important in this case is to define your positive and negative directions. So in this case, it was easier for calculation wise to label my positive direction as going down. This way I could make all of my variables positive. You can label the positive and negative direction whichever way you want, but you just need to stay consistent. So it would basically make either all of my values negative or all of them positive. Did that answer your question? Awesome, great. Yeah, and we'll also share the slides. So if you guys want to reference them later on, you can do so. All right, great. If there's no questions, thanks again for everyone for coming. And yeah, we will share these slides.